So one of the reasons we study Laplace transforms is to learn how to use them to solve initial value problems. So we're moving into section 8.3. So here's an outline of the process that we follow to solve initial value problems with Laplace transforms. So we start out with an initial value problem. We're going to take the Laplace transform of both sides of the differential equation, and we're going to obtain an algebraic equation in S. So you first start out with a differential equation where t is the variable. We're going to take the Laplace transform and it will be in S. And we're going to solve this algebraic equation for y of s, which stands for the Laplace transform of little y of t. Once we find it, then we're going to take the inverse Laplace transform to get back to little y of t, which is the solution to the initial value problem. So the first thing we need to do is to learn how to take the Laplace transform of the first derivative. So I'm going to go ahead and tell you what it is. The Laplace transform of the first derivative of little f prime of t is equal to s times the Laplace transform of little f of t minus little f evaluated at 0. And we're going to get used to this notation. We're going to call the Laplace transform of little f, we're going to call that capital F, and it's going to be a function of s. So the Laplace transform of the first derivative is given by s times the Laplace transform of little f minus little f evaluated at 0. And again, we're going to be solving initial value problems, so little f at 0 will be a given value. So let me help you understand why this is true. So by definition, the Laplace transform of f prime is the integral from 0 to infinity of e to the minus st times f prime of t dt. So we're just using the definition of the Laplace transform, where instead of using f of t, we're taking the Laplace transform of the first derivative. So this function goes there in the definition. And we're going to integrate by parts. So this is u, and this is dv. So if that's u, its derivative, remember you're differentiating with respect to t, so the derivative is e to the minus st times the derivative of minus st with respect to t, which is minus s. You just treat the minus s like a constant. If dv is f prime of t dt, then v is its antiderivative, it's just f of t. So I've rewritten that in this little box up here. So this is where we were. So this is an improper integral. We're taking the limit as m approaches infinity, just like we did when we used the definition earlier. The limit as m approaches infinity of the integral from 0 to m of the same integral. Now, here we're using integration by parts. So in this expression, this is u times v. So here's u times v. So e to the minus st times f of t, and this is a definite integral, so it's evaluated from 0 to m. Then minus v du. So here's v du. So what happens when you say minus that integral? You have a minus negative s, that becomes plus s. I can pull it out in front of the integral because s is like a constant with respect to t. And I have e to the minus st times f of t dt. So that's the last part of the expression. Now, what does this represent? That's the definition of the Laplace transform of f of t, which we call f of s. Now this first part, we're going to plug in the limits of integration. We're plugging in for t, so we get e to the minus s times m times f of m minus e to the 0 times f at 0. We've just plugged m into this expression minus what we get when we put 0 in there. Now, e to the 0 is just 1, f at 0 is a given number, and we're taking this limit as m approaches infinity. What happens, as long as s is positive, this e to the negative sm power is going to go to 0. And f of m is just, it's not going to do anything to make it not go to 0. So from this expression, This part goes to 0. Here we just get minus f at 0, that part right there. Then we have plus s times f of s. And so that's the proof of why this is true. I just wanted you to know that it's just based on the definition of the Laplace transform. So what will you be doing with this? So we can be given an initial value problem. So here's the differential equation and the initial condition, and we can use Laplace transforms to solve it. So just like I outlined before, we take the Laplace transform of both sides of the differential equation. So the Laplace transform of y prime minus 4y equals the Laplace transform of 3e to the t. Now, the left-hand side is where we're going to be using the property that we just learned. So the Laplace transform of y prime minus 4 times the Laplace transform of y equals, we can factor out the 3, times the Laplace transform of e to the t. Now this Laplace transform of y prime is based on the theorem we just had. It's s times y of s, where y of s, that capital Y, represents the Laplace transform of little y, minus little y at 0. So all of this is just the Laplace transform of that first derivative. Minus 4, we're just calling the Laplace transform of little y, we're calling it capital Y of s. This is a function of s, equals 3, and the Laplace transform of e to the t is just 1 over s minus 1, because this is e to the at, where a is 1. So here you're just getting, you have an algebraic equation, and you want to solve it for y of s. So this part was 0, so you have an s minus 4. You can factor out that y of s. You're just left with s minus 4 times y of s equals the expression on the right. And then we just solve for y of s by dividing both sides by s minus 4. Now, that's your Laplace transform. To find little y of t, we just need to find the inverse Laplace transform of this expression. So here we're just taking the inverse Laplace transform to find the solution. Now again, this is based on what we just studied. We have something that we don't see in our table of Laplace transforms. We need to use partial fractions. We have the product of two linear factors. So we just write it as a constant over the first factor plus a constant over the second factor. Multiply both sides of the equation by that denominator. So when you do that, the denominators cancel. You get 3 on the left. Here, the s minus 1's cancel. So a gets multiplied by s minus 4. Here, the s minus 4's cancel. So b gets multiplied by s minus 1. Again, when you have linear factors, you can pick out the numbers that make each factor 0. So if I put 4 into this factor, this one goes to 0. So I get 3 equals a times 0 plus b times 4 minus 1. That just gives me 3 equals 3b, so b is 1. If I put 1 in for this factor, it'll go away. So I get 3 equals a times 1 minus 4 plus b times 1 minus 1. That's just 0. So I get 3 equals minus 3 times a, so our a is negative 1. So we're just going back up here and replacing the a with negative 1 and the b with 1. And that's what I've written here. So each one of these expressions are real simple inverse Laplace transforms of the form 1 over s minus a. Here the a is 1. Here the a is 4. You have a negative 1 here, so it's negative 1 times e to the t plus e to the 4t. Now just think back to how we solved this problem several months ago when we were all together. So here was the initial value problem. This is a non-homogeneous first order. We first found the homogeneous solution. We just said that was a constant times e to the 4t. Then this was non-homogeneous. Our little f of t function was 3e to the t. The associated set of functions was just e to the t. Was e to the t in our homogeneous? The answer was no. So our particular solution was a e to the t. Don't get these a's confused with any a's above here. We substituted into our differential equation by taking the first derivative. So the first derivative of a e to the t is a e to the t. So when we substituted, we got a e to the t minus 4ae to the t. When you simplify, that's minus 3ae to the t. And that's supposed to equal 3e to the t. So this time, minus 3a is 3 and a was negative 1. Again, it had nothing to do with the a above here, but it just happened to turn out to be the same. So the a in our particular solution was negative 1. So our particular solution is just minus e to the t. We found our general solution by adding the homogeneous and the particular. We plugged in our initial condition. So that would say c times e to the 0, which is 1. So c minus 1 had to be 0. So here c was 1. So we replace that c with a 1, and we get e to the 4t minus e to the minus t. Or sorry, e to the t. And that's exactly what we got above. So using Laplace transforms just gives you another way to solve initial value problems. We learned how to do many of these in the past, but I just want to verify that the answers would match up.